Hello, I'm Robert Walker, and this is to outline the central point of my preprint. I plan to submit this to Astrobiology Journal at some point, this spring probably. And first of all, though, I want to share it with experts and ask questions. The idea is to get feedback, to see if I'm missing something, and to see if there is anything to be corrected, anything that isn't quite right in it. It seems pretty clear to me, but see what you think. So first of all, NASA does have to protect Earth. Nobody questions that. And the main thing that is a little bit that you might wonder about is this 19 years time period. Because the planetary protection literature usually says that that's 11 years. So where do I get 19 years from? And so that's the central point that I want to talk about in this presentation just now. So what I found is that the NASA's proposals are likely to meet objections. It's likely to be based, we don't know what they're going to propose yet, but it's likely to be based on the published designs for a Mars receiving facility, and I found that those they do not comply with the likely legal requirements. And so once it gets independent scrutiny by experts from other agencies and disciplines, NASA, it's likely to get objections, and this means that NASA can't know what they will build until the end of the legal process, because these objections could come at any point. And so why weren't they delayed in 1969? And the answer is that in 1969, NASA, there was no public process, and NASA were able to overrule very serious objections to their proposals because of the way things were set up. But today, there will be a legal process, and there will be open public debate and peer review, so they won't be able to do the same thing that they did in 1969. Because in 1969, nobody outside NASA and this interagency panel knew what they were proposing until the date of launch of Apollo 11, leaving no time for any public comment or objections. And that's not permitted today. And so, for this reason, NASA can't know in advance that its proposal will pass legal review. And they're not permitted to risk public funding, especially at the huge cost of this $500 million. They can risk small amounts of funds, but not this level of funding. So the build has to start at the end of the legal process. Again, am I missing anything here? Any of you who are expert on NASA and the legal process and the funding and so on, I can't see any way that they're going to be permitted to risk $500 million. And then even if they did, then there's no way they can guarantee that what they build will be accepted at the end of the legal process. So they could build this facility at cost of $500 million, and then 8 or 9 years from now, they discover they should have built something different, and so then you would still have to add the 11 years onto the 8 or 9 years of the legal process, and you'd have this extra facility that is of no use for returning the sample. So what we have established is that NASA does agree they have to protect Earth from unsterilized samples, and they hope to pass key decision point A, and perhaps they will, because that's just NASA talking to NASA. But I don't see how they can pass key decision point B, which is the very detailed, where they've got to have architectural plans and everything, especially if the legal process has already started and it's become clear that they're going to have objections. And the estimated minimum timeline for the legal process is 7 to 8 years. But that's based on 6 to 7 years for the EIS and 2 years for the consensus legal position before you start. But the legal process is likely to extend well beyond that. I can't see that actually working, because as a result of the objections that I've discovered that I'm sure are going to be filed. And these are all the agencies that are going to be involved. And then the EU, ESAs are partners, so of course the EU legislation is involved. And it may well be the legislation of the UK and Canada. And then there are going to be international treaties that are going to be triggered, and international organisations like the World Health Organization. And at any point during the legal process, any of these could raise objections that nobody has thought of before, which would then have to be considered carefully. And so those objections could easily extend the legal process. For instance, when the World Health Organization gets involved, then if it hasn't been raised before, there's the possibility if a technician, through some mistake, gets contaminated, then there are questions of quarantine. And the planetary protection literature has not looked at the possibility of a symptomless spreader. So how can you use quarantine to contain some opportunistic Mars pathogen if the person who is first infected is symptomless? And then there's the possibility of pathogens that could harm Earth's other creatures and not human beings. But yet and there's an example, for instance, of the astronauts, and they carried a mold, a fungus to the ISS. Even with their 2-week quarantine and everything, there were no symptoms. It is a fungus that can be pathogenic on humans, but wasn't in this particular case, opportunistic pathogen. And so there were no symptoms, no sign of anything, but the 2 of the zinnia plants on the ISS died of it. So that also shows that you could easily have things in the sample that are harmful to other organisms in Earth's biosphere and that do nothing to humans. And again, how can you keep them out with quarantine? So these sort of questions will be raised. It's very likely all the facilities that I've seen, recent designs, relied on technicians handling the samples with gloves in glove compartments, and then these could have, and there could be a breach of that, there could be damage, there could be some problem with the filters, they need to be repaired, and any of these could lead to a breach that would lead to a technician then having to be quarantined, but then quarantine doesn't seem to work. I think that's going to be the end result of the legal process. The quarantine used by Apollo was never given any legal review, or any peer review either. So that's one of the objections. Another one is the actual filter technology. So if you actually look at the 2012 European Space Foundation's sample return study, now this is the most recent study, is surely going to be considered in the legal process, and I expect their recommendations to become legal requirements. So one of their recommendations was that there shouldn't, a particle of 0.05 microns or larger shouldn't be released under any circumstances for the entire duration of the facility. This is well beyond the regime where you test HEPA or ULPA filters. This was because of the discovery of starvation-limited nanobacteria, which get very thin and they can pass through a 0.1 micron nanopore. And none of the published designs for a Mars receiving facility satisfy this requirement. They all use HEPA and ULPA filters. And what's more, I looked to see what could they use if they don't use those filters, and there's nothing. There are no filters that are actually certified to be able to keep out everything at 0.05 microns. Not only that, there isn't even an experimental filter in a laboratory that could do that. The best experimental filter I found could keep out 88%, in other words 12 out of every 100 would get through at that size range. And that's the best available technology at present. So that's an objection that NASA's proposal is certain to meet. And there's no way that they have something that they're going to propose that will pass that requirement. And so how are they going to deal with that? But there are many other issues, and for instance, synthetic biologists, they consider that biosafety level 4 facility is not secure enough for their discipline. Because you do, of course, get leaks from even the best facilities. There's also a possibility of accidents, like a plane crash even. Very unlikely, but it can happen. Light planes do quite often crash, and one of them could crash into the facility. Is it designed to be safe in that situation? What about a mistake during retrieval of a sample, or terrorist or criminal action? So they design their synthetic biology so that it is dependent on chemicals only available in the laboratory. That's an impossible solution for us. And then their level of safety that synthetic biologists require of basically no appreciable risk. And that is also Carl Sagan, then he said that we shouldn't take even a small risk with 1 billion lives. So this could easily be what is decided in the legal process. If that is the decision, then we have to use the more stringent prohibitory version of the precautionary principle, where we can't return the sample if there's even a small but appreciable risk of harm. In that case, then we simply can't do it with current technology. Return an unsterilized sample which could have life in it that we don't know its capabilities. We can keep out life if we know what's in it, we know what its capabilities are, we know what needs to be quarantined, but not if we don't know. And so, as I explained, they could be confident in 1969 because there's no legal process. And there were very serious objections. The National Academy of Sciences and the National Health Service, they both said that there's essentially no protection of Earth with their plans, because the astronauts, they returned the astronauts. The first breach of containment was when they vented it during the descent into the atmosphere. The second was when they opened the doors of the capsule, bobbing them out on a heavy sea. The astronauts got out onto the capsule. They did wear biological garments to try and contain, but there would have been dust on the outside from inside the capsule. The waves were actually splashing them when they were in the dinghy, while they were trying. Buzz Aldrin talks about how the waves were crashing over and splashing them as they were wiping themselves down with a bleach solution, which was how they were supposed to sterilize themselves. But only a few seconds, and you need 10 or 20 minutes of bleach to sterilize, for instance, anthrax spores. And then when they'd finished that, they weighted the cloths that they'd just been wiping themselves with, the outside of their garments, and they dropped them into the sea. And after that, there was really no protection of Earth from whatever life there might have been in the samples returned from Earth. So also this history of what happened last time NASA was responsible for protecting Earth from materials returned from the Moon, this will lead to there being very careful scrutiny of whatever their plans are this time around. So it's the other way around. It's not going to be a precedent. It's going to be the opposite of a precedent. It's going to be a reason to be very, very careful and look very carefully, because they said back then that NASA just didn't seem to be taking any care to protect Earth. They didn't seem to understand the importance of protecting Earth. Some of the experts in this interagency review, and they very strongly objected to that, but NASA was able to overrule, and NASA said, well, we have this timeline, we've got to get it ready before the Apollo launch, we just can't do the modifications that you're requiring. And so they just went ahead with it. So this will not be permitted today. We are much more aware of such things. So the consequence is, well, I don't think they're going to do this. At some point, they're going to realise they just can't complete this legal process and then complete the build in time. The only question is how far they get, and whether they even get as far as starting the build thinking that they're going to be able to pass the legal process. But at some point they're going to realise that they just can't do this. And so this makes 2040 the earliest date, but I don't think they're even going to do this. And then it's the same with ESA. Then ESA also, they have to know what they're going to launch when they launch their spacecraft to Mars. And if this legal process is going on, they won't know what the requirements are on their orbiter or the Earth entry vehicle. And they need to know that before they launch. So again, that's another reason, and really that's going to come up pretty soon, that they're going to realise at some point that if they do an unsterilized sample back to Earth, then they simply don't know what to launch to Mars until 2028, 2029, and then it's the same sort of thing as with a Mars receiving facility, that it takes a while to design and build a spacecraft, and it's not easy to modify it if they decide different requirements are needed, and they have to start again. So it's 2028 to 29 before the start of the build of this spacecraft to send to Mars. Or it could easily be. And they have the same problem as NASA. They could build this spacecraft, it could be all ready to fly, and then from the legal process they discover that what they built is not the right thing, and they have to start again. So I don't think either ESA or NASA are going to go ahead with this. It just makes no sense. So the simplest solution, so the experts in NASA, most of them, are of the view that there's no present-day life on the surface in Jezero crater. So they don't think there's going to be any life in the sample. They don't know, they can't prove it, that's why they have to protect Earth. But that is their opinion, that's their belief. If that is your belief, then the simplest thing is just to sterilize it, because you don't think there's going to be any life to be sterilized. And you would recognize it as life, if on the very remote chance there is something in it. And this is not likely to damage past life, because on the most likely scenarios, anything they return has had far more than a sterilizing dose of cosmic radiation. Indeed, it's likely to be sterilized to such a point that past life is unrecognizable. And it's especially mixed with organics from meteorites and comets. There is likely to be reasonably pristine past life on Mars, but finding it will be very difficult, and Perseverance doesn't have the necessary tools to search in situ for biosignatures to find these pristine samples that probably do exist in Jezero crater. So this means that it's very unlikely the science value will be seriously damaged if there is no present-day life there, or in Jezero crater, or if there's only a small amount of it. However, in my article I do suggest ways that we could, so there's very intriguing Viking results, for instance. Now, the two possibilities, one is that it's life. It's very difficult to understand because the peak of the evolution of the radioactive radioisotope labelled gases, radioisotope carbon labelled gases, was the peak in the daily cycle of temperature changes is delayed by 2 hours. And a 2-hour delay is very hard to explain with chemistry. 10 minutes is explainable, but 2 hours strongly suggests circadian rhythms. There were other puzzles. For instance, whatever was in it was inactivated by being kept in darkness for 3 months. And that is very hard to explain with chemistry. And so, if it is chemistry, it's some very complex, unusual type of chemistry. And if it is life, then that is of course great interest. But either way, if it's some complex, unusual chemistry, maybe protocells, or maybe something, just some very complex organics, some very complex kind of reactions that are very hard to simulate because we don't know what's in it, then this is of great interest. It will, first of all, it'll tells us what happens on a planet that doesn't have life, if it isn't life, or that may not have life. Or if there is life there, but it's not in this sample, it gives us ways of understanding things that are going to make our searches more complex on Mars. So if it's very complex chemistry, we want to know what it is in order to search for life, and to know what to search for and what to not look for. So it's very important, I think, to understand the Viking results. And the best way to do that would be to return a sample of the dirt from Jezero crater. Return that sample and just a handful of dirt, a scoop of dirt. And then another thing that we could, I think, be very important from an astrobiological point of view is, and I'm very surprised I can't find anyone who suggested this, and this is to send a rotary airborne sample collector like they use to look for microbes in the air. And anywhere where there's life on Earth, you get spores going off into the atmosphere. And for instance, in Japan, you can detect spores from the Gobi Desert, in the winds blowing from the Gobi Desert to Japan over such vast distances. So whether, even if they're alive or if they're dead, it seems very likely, if there is life on Mars, that it would propagate via spores in the dust. It would develop adaptations to deal with the very strong, very difficult conditions of the dust storms. But the dust storms naturally filter out UV. I talk about this in the article, various ways that possibly Martian life could adapt to be able to propagate in Martian dust storms. If there is such life, then an obvious thing to do is to try and do some airborne air sampling, especially during dust storms, and to see if any spores can be discovered. And it could also be the spores that they get embedded in a crack in the dust, or they could cover themselves with nanoparticles of iron oxides to protect themselves, and the various other possibilities. So these are two samples that we could add, collecting the dust, and we could also just collect dust that falls even without a sample a vacuum system, but just sample dust that falls into an open sample tube, or falls into the Mars capsule. Just hold the Mars sample capsule, leave it open on the surface enough time for dust to fall into it, and return a fair bit of dust, and also return a scoop of the dirt, and then put the sample tubes on top. Something like that, or the other way around, all that on top of the sample tubes. These would be quite simple, or maybe more complex, but these would be modifications that are possible for the ESA-FETCH rover that I think would hugely increase the possibility of returning something of astrobiological interest. I also suggest ways that the Perseverance rover could look for very young craters, because from the statistics there should be craters that are only a few tens of thousands of years within reach of Perseverance, and these could excavate the surface to depth to 4 to 9 meters. So this may be a way of getting reasonably pristine early life as well. Anyway, if we discover something there that is of great interest, and this could be through discoveries that we make with Perseverance or with ExoMars, or it could be just the reasoning that I'm using just now, leads people to think, oh well, it could be interesting to return a sample that we don't want to be sterilized. That's when I suggest we return to a safe orbit. Now, have a particular orbit, I don't want to, I talk about this separately, but there's a particular orbit which would be a very safe place to return it to, maybe about 50,000 kilometers or more above geostationary Earth orbit, and in Earth's ring plane if it had a ring system. It's a very safe orbit in terms of no risk of contaminating other satellites or Earth. So these solutions can be done with no risk to Earth's biosphere, and they are as straightforward as the sample returns we have already done for comets and asteroids. So if we do it like this, we would not have this legal process, because we only ever return unsterilized materials to Earth. Even if we return to above geostationary Earth orbit, then we have subsamples we can immediately return within a few weeks to the terrestrial surface, and these would be sterilized, so again, no legal process. no legal process for back contamination. I mean, of course, legal process for other things like where there's a risk of the well, the usual processes you use for any space mission, but it wouldn't be anything more than those, like the risks from the launch or risks from re-entry and so on, or just as for any space mission. So it'd be very straightforward, just as straightforward as the samples we've already returned from comet and asteroid samples returns. So that is my proposal. The article itself goes into this in a great deal more detail. A lot goes into many more things than this. This is just the central point to explain the reason for. So if I go back to this is basically explaining the title and the 19 years and a proposal to sterilize the samples. So in fact, why not just read the title at the end of it? So NASA has to protect Earth from unsterilized Mars samples with a minimum of 19 years for modern legal process then built. It's actually likely much more than that. Proposal to sterilize samples or return to a stable orbit above GEO to study with teleoperated instruments. And then just to say for the instruments, then the astrobiologists have designed exquisite instruments that they want to send to Mars at some point. Very lightweight things that can detect just even a single amino acid, or that can, in a gram of sample, they can do genetic sequencing with something you could hold in the palm of your hand, end-to-end genetic sequencing if it's related to terrestrial life, and so on. These they could send up to this orbit above geostationary Earth orbit and study the sample there just as they would on Mars, but without the latency. So this could also be a first step towards sending these instruments to Mars, doing it first above geostationary Earth orbit. And then we can have a very quick turnaround and send new instruments up there if we discovered something new needs to be investigated. And by the time that this would be happening in the 2030s, we could send huge masses up to above geostationary Earth orbit, and we will have much better telepresence than we have already, which is already fantastic. And it will be almost like they are up there studying it themselves, but it's through remote telepresence. So I think this is by far the best way to do it if we do think there's a possibility of life in the sample. And meanwhile, for human explorers, I don't think we're going to be having human explorers anywhere near Mars by the 2030s. I think it's just far more massive a challenge than people realise. I go with Hadfield, who's the ex-commander of the ISS, and he thinks it's going to be the next generation before we send humans to Mars. We're going to have a huge challenge already with humans on the moon. We haven't yet returned to the moon. This is going to be the big challenge for human space exploration in the next decade. And it's great to have your sights set into the far future and thinking about Mars, but I don't think we're going to be doing that as soon as the 2030s, probably not as soon even until the 2040s, because it's such a difficult thing to do. As Chris Hadfield said, if the Earth and the Moon were threatened by some unimaginable catastrophe, I can't remember his actual words, I've got the quote in my paper, but that we could send, and probably nearly everyone would die, but we could send people to Mars. But short of something like that, then we're going to be on the Moon, and we're going to have this a big enough challenge with just a few days, with 2 days emergency return in case of an accident to Earth, and emergency supply from Earth with a 2 days delay if there's something that you're missing and so on. That's going to be a huge challenge. I don't think people realise quite how big a challenge it will be to have an outpost on the Moon. And I think it's be towards the end of the 2020s and into the 2030s before this becomes like something that we do almost like routine, and we have people shuttling back and forth, and it becomes just like Antarctica or something. And then at that point we might start thinking about it being safe to start looking further afield with our technology better tested. and then the many other places we can go other than Mars. And if we go to Mars, then we can be in Mars orbit, studying the surface by telepresence. And I think those will be the first human missions to Mars, and humans could be of great value in finding out what is there. And then one of the points I make in my article is that we don't know that whatever life on Mars is safe for Earth. One possibility is that Mars has mirror life. And if Mars has mirror life, then it will never be safe to return that to Earth, to mix up with our biosphere, and it will likely never be possible to quarantine a returning Mars astronaut from Mars to Earth in such a way as to protect Earth. So we have to bear in mind we don't know what is on Mars, and our decisions have to depend on what we discover there. And the prospective Mars colonists should be as keen as anyone to find out what is on Mars, so that we can make the correct decisions to protect the astronauts, to protect whatever's of interest on Mars. And if there is interesting life on Mars, then, and even if it's feeble life that would be destroyed easily by terrestrial microbes, this would be a very strong motivation for Mars colonization in orbit, Mars settlement. Very strong reason to be there. It's very hard to come up with a reason for humans to be on the surface of Mars that would actually could be paid from Earth, but life on the surface of Mars, then we could exploit it also by telerobotics and sterile facilities on the surface of Mars, and then export things from Mars to Earth. You don't need to have humans on the surface of Mars to export and to exploit Mars. So this is not saying hands off and you don't do anything to Mars. It's saying find out what's on Mars, make the wise decisions once you know what's there. So anyway, I will upload this and then hopefully I'm very interested in the paper. I'll put the link to the paper in the video description. If there's something that I have made, some mistake I've made in this, please let me know. If there's something I'm missing, if there something that needs to be added, and if in particular, one of the most central points to my paper is this 19 years timeline. So if there's anything that I have not understood, that I've missed in terms of the reason why there's a 19 years, where I come up with 19 years instead of the usual 11 years, then please let me know. I have talked about this, I've asked people, I haven't come across anyone yet who sees any problem with this timeline. And I can't find anyone who has found a way, who has said that it would be shortened and that it can be done in parallel. So, but I haven't really asked very many people yet. So that is one of the main reasons to do this upload, and to try and invite questions from experts. And basically my paper is hugely multidisciplinary, and that's the main reason I come up with different answers from the planetary protection literature, because I've widened the net of the types of literature that I've looked at hugely, like synthetic biology, like the engineering of filters, and the Mars, the NASA procedures, and that also means, though, that it touches on a vast number of different disciplines. So now that I've got the paper, it's just about finished now in its present form. I am now going to be emailing, I'm going to be asking permission for the figures, and that will be a good opportunity to also ask the experts, have I summarized your figure properly? And then I'm going to try contacting experts and see and get feedback and see in different disciplines, like for instance the people who designed the filters that I talked about, and have I correctly summarized the situation that the technology doesn't exist for the 0.05 micron filters. So there's quite a lot to be checked before I will be submitting this to a journal. And so, and also, so too, please bear in mind, this is a preprint. This is not in its final form. This needs to be very thoroughly checked now to make sure if what I've said is correct. But I think it does raise lots of interesting questions that do need answers. So I'll upload this now.